mean, you can use some CAD tools to extract out the capacitance and find out. But when you are starting from scratch, you don't have any simulator or anything, then you just assume the sizes of the input capacitances of those paths. Because, okay, what happens is that in a large design, you cannot optimize every path in the world. Which path do you optimize? Huh? Critical path. What is the critical path? Anybody? What is the critical path? Longest path, right? So, if you have a pipeline arithmetic logic, then you'll have to see between the different registers, the combination of circuits, and which has got the longest delay, right? And that will decide what will be your clock frequency is. Because if your clock frequency is higher than that, then this is not going to be computing correctly. Now, just because you have other stages smaller and one stage big, you cannot say that, okay, I will just increase the clock frequency a little bit, right? Because then your computation will be wrong. So that's why in any system design, first and foremost, you have to find out what is the critical path. And we are trying to optimize the delay of the critical path because that's going to be the, now all this branching thing may be smaller delay, so we don't really care if the transistor is optimized or not, actually, right? Because in a pipeline adder, all the stages have to compute simultaneously, then only you can move on to the next, you can bring in the next data set, right? I mean, if you are saying loading the pipeline with different data sets, so whichever stage has got the largest delay, that will decide the clock frequency, correct? So basically, that is what the idea is, that when you're doing the manual design, you're trying to apply this for the critical path, the longest path. So when you do the longest path, you can make some sort of, unless you know the values of those other gates, their actual capacitances. If you don't know, you can estimate their value and try to optimize this one. But again, this is again crude. You'll have to go back to the simulator, you'll have to do all those things, but you do it in the different stages. Do you follow? Because you cannot go into SPICE without knowing the sizes of the transistors. You have to put in the value of the transistor, then only SPICE can calculate, right, the delay. So how do you find out the size of the transistor? This is how you do it. Yes?
So, like you were saying that, is this, in application, is it more useful to find like relative sizing?
What's that?
Like, because you're saying that, like we're given the, for example, input capacitances for like the initial one, and like we might not even have that going in. So are we just to assume something and then continue with the analysis and then?
No, in this example, we know the critical path is between this and this, and we know the capacitance here and capacitance here, and we're trying to size the transistor such that the delay between this and this will be minimizing, right? That's what we're trying to do here.
Right, but
how do you know what the capacitances are, right?
Yeah.
That's where the, say you are driving a large wire here. So that wiring capacitance is 108 plus the capacity capacitance of this. Similarly, this is coming from some inverter or something like that. So you know that the input capacitance of this and the output capacitance, so from there you're estimating. That's all. Any other question? Do you like this stuff? No?
Seems extremely like simplistic, honestly.
What's that?
It seems sort of simplistic the way you presented it.
Well, I mean,
might be that
It's
way.
the easiest way to sit in front of computer and do everything, right?
Yeah.
But the problem is that when you go to industry and when you have to do things fast and you have to apply your engineering expertise, you have to have some framework to apply to design your stuff. You just cannot go to the computer and simulate because that takes a lot of time. Time is money, right? So how do you optimize your time, money, and the design, correct design? So this is an important step for that actually. Okay, so these formulas look more complicated, but they're very simple. All you have to just understand that you have to find out the logical effort of this gate, this gate, this gate, multiply together, you get the value G. There is no branching here. If there are branching, then you just multiply the branching. H is from here to here, and then you find out the estimated value of the path effort. Path effort is F, which is the GDH, and then you find out the individual path effort, and from there you find out the delay. So we have done this. Now, often you try to reduce the delay by adding some extra inverters. So if there are n1 stages in your actual logical circuit and you add n2 inverters, which is equal to capital N multiplied minus n1, then each stage will add some delay, the parasitic delay. But you'll find out that even if you add the parasitic delay of n2 inverters, the overall delay can be minimized. And we'll see some example that even though it is counterintuitive that how I can reduce the delay by adding inverter, but I will show you some examples that it really reduces the overall delay by adding some inverters. Anybody has some guess why it is so? Intuitively. I'm not asking you to calculate. How do I reduce the overall delay by adding some inverters, which will be adding some extra delay, right? Anyway. Yes?
It kind of splits like the driving load between a bunch of different devices. So
It reduces the individual effort, right? The stage effort, because now n is equal to n2 plus n1. So the individual effort is reducing. That's how it is. Now, this is a table just to show you that if the path effort is these values, how many stages are required, each stage is what is the effort and what is the delay. So this is kind of, people just use as a metric when they try to design their circuitry. So just keep this in mind. Now, we have gone through this. I just want to recapitulate that there are two things. One is the gate level, another is the path level. The gate level, we use the gate logical effort, gate parasitic delay, C out of C in of the gate, then the delay is given by this. For path, we find out the output path at the output and input value of the capacitances, then all the logical efforts of all the gates of the path, and then the branches at different points, and then we calculate the overall branching effort, which is the multiplication of the different branching values. So the total path effort is given by this. So this example is for this, and earlier we computed for a single gate level using this. So keep that in mind, that don't get confused with all these different symbols. These symbols are very simple actually. So what is the method? The method is that you compute the capital G by looking at all the gates, finding out their logical import of that depends on the structure. Find out the branches, multiply this, find out the C out and C in, find out this, and then optimize the state import by using this formula, and then the delay is given by this, and then you use this thing that we mentioned over here to size the transistor. So that's all you are required. As a designer, you have to specify what should be the values of these transistors so that your salaries are very high. So obviously, if you are in a big company, you may not be asked to do the simulation. You may have to just give it to somebody who is less expensive, right? So, but they need these values, and that's why you come into play. You provide the values, and then they do the simulation. Now let's see two examples. The address decoders, which we talked about for the register 5, will be optimizing with respect to delay and with respect to the layout area. So the address decoders, we have seen that it drives these long lines. For that, we need inverters, which should be sized by 10. So these are the sizes of the